Find the sum. Now notice we're going to repeat the two that we just did. But we notice that in this particular instance, we're going out 15 terms. I start at 1 and end at 15. It's the first 15 terms. So n is going to be 15. A sub 1 is going to be 3/9 or 1/3. And then R we said was going to be 3. So that S sub 15 equals A sub 1 times 1 minus 3 to the 15 divided by 1 minus 3, which is 1/3 times 1 minus 3 to the 15 all over -2. Now you could actually stop here and do it if you were careful how you put it in your calculator. Which is 1/6 negative times 1 minus 3 to the 15th power. So here we go. 1 minus 3 to the 15th, the numerator. Divide that by -6, that's the denominator. And notice 333, whoops, I'm sorry about that. 3333, that's 1/3. So it's 2, 3, 9, 1, 4, 8, 4, and 1/3. These are going to be not pleasant numbers. We're already at 15 terms. So it's 2, 3, 9, 1, 4, 8, 4. And if you wanted to say 0.33, I'd accept it. And it's 1/3. And so 2 million. Or what you could do, well, of course, that's not going to help much, to push that to a fraction. Because it's not going to be pleasant if I push that to a fraction. So let's see. Math. Push it to a fraction. And it can't. Not enough information. Not enough decimal. Not enough places. Again, this one starts at 1, ends at 15. Now, I'm not going to throw anything wonky at you, like starting at 2 or starting at 3 and ending at 15, where you're dealing with arithmetic and geometric. You got a whole different animal on your hands. So, what do I know? I know that I need A1. N is 15, and R is 3. So A1 is 4 times 3 to the 1 minus 1, so it's just 4. So I know that S sub 15 equals A1 times 1 minus 3 to the 15 all over 1 minus 3, which is 4 times 1 minus 3 to the 15 over -2. And then we said the -2 reduces out with this guy, giving me a -2. Whatever point you choose to do the work, it's up to you, times 1 minus 3 to the 15. Now, I already did a 1 minus 3 to the 15, and if you have the color calculator in particular, or you could try this, if I just go up what's called the stack, I can just pull that off when I hit enter. That brings that down. That's going to be helpful, by the way, in 9.6 if you have your calculator that will do that. If not, you can do second enter, second enter, second enter, and do that. And on this guy, you can actually do that as well. You can go up the stack. And it's that. Now I'm going to multiply that by -2. And there it is. They're not small numbers. So 286,97812. So it's going to be 28 million.
So this could be used for like how many carcasses of animals over a function would we see?
Yeah.
Okay.
Well, the other thing is that it's used quite frequently in population. Population growth. You know, you're going to expect big numbers at a certain point in time, and you're going to say, why would that be? Because remember that the exponential function looks like that. And you're going to be adding bigger and bigger and bigger and bigger and bigger numbers. So the sum is going to get bigger and bigger and bigger and bigger and bigger.
And by the 15th generation, like
it's
15
huge.
generations ago was like,
yeah,
like almost BC.
Yeah, and see what happens is once you round that bend, it gets scary because the function takes off.
Right.
So when they talk about bending the curve, whether you're talking about population or whether you're talking about when we're talking about healthcare costs, if they're growing exponentially, it's scary. Because once it rounds that curve, it's going to take off if that's how it's going, because it's just going to multiply on top of itself rather rapidly. When they talk about bending that curve, it's like taking this guy. What they want to do is they want to slow down the growth. So it's like taking the arm of that graph and pulling it down so it's not growing so fast. That's what they mean by bending that curve.
And that's a
So the cost
multiplication outside of the parentheses, right?
It's going to be, what you're now going to be looking at is a horizontal stretch or vertical shrink.
Right.
You got to have something that's going to lay this thing out more slowly. So exponential functions can be good or bad. If it's your money, it's good, right? During the tech boom, back in the, whatever it was, 90s, I guess, 80s, 90s. You know, you had Microsoft and you had, what we called high flyers. At that point in time, they weren't stodgy companies like they are now. They were pure growth companies and growing rather rapidly. The price of Microsoft stock grew exponentially. That's how Bill Gates became so rich so fast. Because if you look at over time, the price of the Microsoft stock actually looks like an exponential function. And once it go up, well, now it's a stodgy company, so it's not growing so fast, and you have more variation in it. It's kind of calmer because it's an old, by standards, it's an old company, and it remains an old company unless it's innovating all the time. That's what's going to happen with Apple at this point. With Steve Jobs gone, what's the next innovation?
Cars.
Something. Well, yeah, they're looking at that too. So yes. So here we go. Last one, we're also at 15. But notice R is what? 3/5. So I expect the number not to be huge, but tiny. So that A1 is 2. R is 3/5. N is 15. So S sub 15 is A1 times 1 minus R, which is 3/5, raised to the 15 power, 1 minus R, which is 3/5. So now, again, I take my handy-dandy calculator. And if I want to put it all in at one time, which I don't like to do, but it's parenthesis 1 minus, R happens to be 3/5, so it has to be in parentheses, to the 15, parentheses, so that's the numerator. You know why now I do it in pieces, divided by 1 minus 3/5. That's the denominator. And then multiply that by 2. And it's approximately 5. And you come right down to it. That's a far cry from 28 million. And then we will